Okay, guys, it's time to start, and today we'll talk about like another Kaggle problem. In some sense, I would like to say that it's not first time that I'm talking about some kind of top solutions at Kaggle, and I'm happy that I talked to you, like to some of you guys, and previous times it was just like people that heard Kaggle but never participated. But this time, I believe like many of you have some like domain knowledge in a way that you try to work on the problem that I will talk about. I mean, worked with data and tried like and got all this pain. And okay, so to start with, how many of you do you have any Kaggle masters and grandmasters here? No. Okay, I am Kaggle master. Okay, how many of you tried to work on this problem about satellite images and did at least one submission? Okay, this is good. 3 can be better, can be worse, but 3 is fine. Okay, how many of you tried to do any submission on any Kaggle competition ever? Nearly everyone. This is great. This is really great because last time I was like talking about all-state competition in the like H2O company, and when I asked this question, only 3 people raised their hands out of 80, and all these 3 people were working in this H2O. So all these like visitors, they never tried to work on Kaggle. And okay, time to start. So my name is Vladimir. I work as senior data scientist in the startup named Trocord here in San Francisco. Today I'll talk about our solution to the problem, to some deep learning, neural network, computer vision, and other beautiful words like problem, and I'll present our solution and our approach that we used to get third place out of 419 teams. I mean, we were surprised in a way that at the public leaderboard we were 8th, but then I woke up like next day is my birthday, and it was like a nice birthday gift that we moved 3rd, meaning we were like able to claim our money, and 20,000 in San Francisco probably is not that much, but I mean, still fine. So it was a teamwork. And it was kind of important because I believe that independently, me and my teammate Sergey would be able to get in probably like top 20 or maybe, top 10%. But I mean, when we joined and like started working on this problem together, it became much better. Another thing that I want to emphasize that typically when you work on some problem in some, let's say, startup like industry environment or maybe in academia, in the beginning you find someone, you're both excited about some problem, you want to do it well, and then you start working on this. Kaggle doesn't work this way. Decent amount of people asked me, I mean, like, I'm excited about this problem. I would be happy to work in a team with you. This is great, but it's not a team. In terms of Kaggle environment, 2 people that are excited about some problem doesn't mean that they're a team. Typically for Kaggle, and I'm just like saying this because I was asked this question a number of times, typically the best and most commonly used approach when people form a team, when they are worked on this problem independently, they clean the data, they understand the metric, they understand the issues, they go to some level and they're stuck there. And they believe that if they join, like if some people nearly at the same spot at the leaderboard, they can join their like efforts and go higher. And this is the most efficient way. And I believe if you ask some other Kaggle participants, this is the efficient way like to like form a team. 2 seniors, 2 people that are experienced, 2 people that perform, I mean, reasonably well, and they have similar performance, they just go higher. And that's what happened with me and Sergey. Somewhere like about like month before the end, we were like in probably top 20, top 30, and we just like wanted to like perform better. And in some sense, it was much better and more efficient. You see, we have different background, we live in different time zones, and it was also very important because I mean 12-hour time zone was really good. I work, I go to bed, I have some ideas, I tell him I'm sleeping, he's checking. Then I wake up, he shares with me this knowledge, we switch, amazing, yeah? So, I mean, I really liked it. So again, back to slides, back to the topic. So I'm senior data scientist at Trocord. My educational background, I have PhD in theoretical physics from UC Davis. I live in San Francisco, United States, and I mean, in terms of Kaggle experience, I'm Kaggle Master. So I participate in more than 50 competitions, some of them deep learning, time series, computer vision, stacking XGBoost, like all type of different problems. Okay, my like teammate Sergey Mushinsky, he lives in Siberia, in this like city named Angarsk, like snow and everything. And his job is deep learning engineer, and his education is bachelor in computer science. Okay, so and this was our starting position as a team. Okay, another thing, like this is again not related to satellite images, but this is mandatory slide that I started adding in all blog posts that I write about Kaggle and all talks that I give about Kaggle. How machine learning and deep learning is related, like in competitions in industry and academia. And I have experience in all three of them, and my claim and my belief that they're barely related. In a way that, sure, you use same algorithms, same math, you just like try to do something in a similar way, write similar code, but because in industry you need something that is interpretable, scalable, maybe small if you deploy it to like mobile devices, and it works really fast, it's one thing. In academia it should be novel, and in competitions you don't care about anything of this. You just want something that is good. You want to get higher at the leaderboard. You want to create model that is the most accurate. And so, in some sense, in the competitive environment, it's it's fine to have a model that should be trained for a couple of weeks in some crazy cloud and things like this. Yeah. So, and I want to emphasize this again because many people that never tried Kaggle competitions, they like to claim that Kaggle is useless, that competitions are useless, and all this knowledge is okay, I don't want to curse, but it's like not that useful in general, yeah? But I don't believe it's the case, and overall, if you're able to combine in terms of your skill set all three directions, life would be great, okay? But I mean, here everyone tried to do Kaggle, so I should just skip this slide, okay? Next one. So what did we have for this problem? For this problem, and I believe this slide that you like see in front of you has the most text of all like the rest of the slides. Everything else will be just pictures and some explanations, barely any text. But here, what did we have? For this problem looked very, when I started looking at this, it looked very similar to the standard image segmentation problem. You take some image as the input, and as the output, you need to predict what class each pixel belongs. In our case, output, we needed to predict like that each to what classes each pixel on the like this images, satellite images belongs. It can be building, man-made structures, roads, track, trees, crops, waterways, standing water, vehicles, all this type. In the train set, you have 25 images. Typically, you may think that like deep learning starts when you have like thousands, tens of thousands, millions of images. But I mean, no. First of all, there's like ways to work with small number of images, and I'm talking about transfer learning. But in this sense, in this case, 25 images is fine. It was enough. Test set was 32 images, 6 in public leaderboard in public part of the test set, and 26 in the private part of the test set. And I'm saying that it's enough because each image was covering an area of 1 kilometer by 1 kilometer. Just imagine how much information will you have in the satellite images of the San Francisco of this like area. Yeah. So okay. So output classes, this number of pictures. What did we have as an input? And in some sense, this was one of their. So how to say it? We spent the most time how to figure out what to do with our input. And reason that I'm saying here, so like if you look at ImageNet or Coco or some other like standard data sets, or maybe some other computer vision problems that you have at the Kaggle at this time, you will see that you just like have RGB images and you just like use some standard techniques to work with them. Here situation is different. Your input data was much more rich because you like use satellites to capture it. You have RGB, you have panachromatic, and you have like images in the higher wavelength. In total, instead of standard 3 RGB channels, you had 20. You had 20 channels as your input. And they have different resolution. They were even shifted with respect to each other, a whole set of different issues with this data. And it was kind of important to figure out what and how to deal with this. Yeah. Okay, so I was talking about, like on this previous slide, that different images, they have different information and they correspond to the different like spectrum. Yeah. And what I want, like, if you look at this image right now, you'll see like this like rectangles at the top. One is RGB, which is like this like visual spectrum, like what we see with our eyes. We see M that overlaps with this, and but it's like wider. It also captures infrared. And what is like I call and what was called in the competitions is A band. And this is just like even higher wavelength. So basically you have like, not just like you see RGB is really tiny part of this, you have something that's much, much wider, much richer. And it allows to do like some tricks that we'll talk about. Okay, so like 2 slides ago, there was a lot of text, like input, output, but it was text. Pictures are much better. So, and as you see on the slide, on the top was our input, on the bottom was our output. Yeah. So, task of this competition and what organizers were looking at, they wanted an algorithm that wanted a problem that takes as an input satellite images in different spectrum, what you see at the top, and we wanted to emphasize that like M band has much lower resolution and A band has like really small resolution, and maybe you even see like some kind of pixels in this A band, yeah? And you just like, your program should consume it and give us an output, something that you can see at the top, where roads, buildings, trees, cars, everything is marked on the pixel level, yeah? So this like what like in one slide, what we needed to do. Okay, so we create a program, we do prediction, but it's not perfect, and we need some numerical measure to say how good our model is. In this competition, organizers use something that is like called average Jaccard index. So prediction was evaluated in this manner. You take each of the 10 classes, for each of them prediction, you calculate what is called in the literature intersection over union, and also which is also called as Jaccard index. You do this for all these 10 classes, and then you take average of this, and this is your result. So basically, in terms of evaluation, all your classes were treated independently, and it was one of the like tricks that helped competitors to perform better, but at the same time, it was one of the issues in the data. Yeah. Okay, issues with the data. So after probing leaderboard and checking like what class distribution is in the test set, we got to this picture that you can see at the right. Yeah. Top part is train set, middle is public leaderboard, and bottom, this like bottom right, is what became available to us after the end of the competition, and this is the class distribution at the test, at the private part of the test set. As you can see, I mean, so after we did this, it became pretty clear that assumption that you can meet in the literature that like typically claims, assuming that your train and test are generated by the same IID, and this allows you to map it to maximum likelihood estimation and all the standard discussion about cross-validation, they will not work here that well. Just purely because this assumption about IID and same distribution will not work. First of all, you can see that, you know, although pictures look similar, but within each class, distribution of the classes is very heavily imbalanced. For example, in the train set, for 1 pixel of the car class, you get 60,000 pixel of the crop class. And typically, you know, at work, you say like, yeah, class imbalance 1 to 100, this is bad. No, it's like 1 to 60,000. Another thing is you can see like train and test, they are different by themselves. For example, this like crops, which are pretty long, it's like the longest in the public leaderboard, in the public part, and like shorter in the train and things like this. So what does it mean? It means so that your train, public and private, they're slightly different. In terms of competitions, it typically means that after competition is over, there's a lot of screams and yells at the like, you know, at the forum that life is unfair, Kaggle is unfair, and I lost like 200 places and I feel bad. Yeah. I mean, and this is happening because people overfeed public leaderboard, or even if they try to do proper cross-validation. You see, you can take your train set, do great cross-validation, and then you assume that you're great, but no, you like get good estimate with respect to the train set. But test is different, so you do a submission and something doesn't match. And there was a lot of pain in these competitions about this. And as you can see, the private set, you know, some people got 100 places, some people lost 100 places. So yeah, a lot of fun. So, okay, back to this. Issues with the data. We have like small amount of the train data. I said that it's enough, and 25 like square kilometers may be decent enough. But if it was, let's say, 500 square kilometers, situation would be better. Situation will be much more stable. Because even here you see that like, you know, vehicles are barely represented. Water you can barely see. Structures and roads also pretty small number of pixels. And this made it harder for networks to learn it. And I think out of these 25 images, out of these 25 square kilometers, data is really diverse in a way that some like set of the images was corresponding to like towns or roads and some kind of man-made things. Another was complete jungles, no roads, no buildings, some trees and bushes and like these wide rivers. And at the end of the competition, it became clear that it's like something in Nigeria, so something that's not familiar to me, something that's happening in Africa. And there are also some decent amount of like farmland, and you feed this all in these 25 images. And so yeah, it makes it harder for networks to figure out and capture like patterns and contextual information when they work with this. There are also decent mistakes in labeling. Like you have some trail, some road that goes and then stops and then continues a bit later. You have, cars and actual data that are like trash cans that are marked as cars and things like this. So data set was in some sense full of it. It can be much worse. So this situation was better, but just small complications to our thing. As I've said, big class imbalance and fact that different distributions in the train and test also added to this. Yeah. Okay, so here I want to show you two images, two pictures with the car. So what do you see at the top? Apparently, yeah, sure. I mean, so private became available after the end of the competition. So I mean, okay, let's just talk about this a bit. So way to estimate class distribution and train and test. I mean, how to do it for this competition. In train, you just calculate it directly from labels. How to do it in test? Because metric of this competition is average Jacquard index, and because in your submission each class has its own line, you can do this trick. You can create a submission. Let's say I want to know how many pixels, what percent of the pixels in the test set corresponds to buildings. What do? I create a submission in which all pixels belong to buildings, just buildings and nothing else. And that's it. You make submission, your answer automatically gives you this ratio because it is Jacquard and because you do one line per, your Wendy, yeah? So basically she's asking because she was admin for this competition and her job was to prevent these tricks that we were doing here. So yeah, in this sense, I believe that she will just next time we will not have this possibility for this leaderboard probing, yeah? Okay, so she says that's fine. Okay, yeah, by the way, guys, if you have questions on the way, it will be easier rather than at the end. So if you have something to ask, just raise your hands and we'll do this. Especially because we have only 30 people here. So yeah, we have this luxury. Okay, issues with the data, pictures. So if you have, let's say, standard RGB images like your dogs, cats, or someone's faces, all these channels RG and B, they were captured at the same moment of time, yeah, at the same instant, but just by the camera. Here, everything was different. When this, I believe, this type of the satellite was taking images, for example, on the top, if you take this M band that had 8 channels, 4 of them were taking at one moment of time, and other 4 couple seconds later. So if you merge them together, you can see pictures at the top. So what's happening? You have a truck, you have a car that is moving. And when you take image of this, when you take a shot, within couple seconds, it's able to move for some distance. And this means that in 4 channels of the M same area, you have this car at one position and in other 4 in another. So you get ghost of the cars. And your task was to label a car on this image, which one? I mean, it added to another thing, it's probably not clear at the bottom, but there we labeled cars and also some debris or garbage or trash cans that just, yeah, increased number of cars on the picture, but again, network was really confused. And I'm saying this because out of the 10 classes, 2 were car classes, and our solution, for cars, we just to drop them and not predict. Basically, we had a bunch of ideas how to implement pipelines and use some kind of faster RCNN and SSD to do some localization in smart ways, but there was just not enough time for this. And at the end of the day, we gave up on cars. And I'm saying this because in some Kaggle competitions, if you just estimate, and probably at work also, that you will not get that much and you need to spend this amount of time. It may be not worth it. Question? No, I said that we had this in plan. So number of cars and the images was not that high, but at the same time we were like able to predict buildings really well. So idea was to constrain our face space from the all like 25 kilometers to something like towns, villages, and roads, and then use like faster CNN to locate cars there and look this promising approach. But yeah, it was time consuming. So realistically, in our final solution that got our third place and 20,000 as a prize, we didn't predict 2 classes out of 8 at all. Yeah. Okay, so let's talk about water. So we needed to predict 10 classes. But like, for example, with water, with running water, there was another issue in the data. Initially, in this competition, there was no water in the train set. I mean, no like running water, no rivers in the train set. After participants pointed this out, 2 like images were moved from the test to the train, and we got some running water, some rivers in the data. But still, like we tried to use neural networks on them, and there was just like plainly not enough data to learn something good. No, we got some results, but they were not that great. After we looked at the literature and we read through a lot of like literature regarding like satellite images, we'll mostly, of course, we are looking at neural networks because it's exciting and interesting. But like another thing is that we couldn't discard and like ignore all this knowledge that was developed before like last 5 years ago when neural networks became popular. And satellite images, they became available like 90s or early and something like this. And there was a lot of research that people made in a way how to analyze satellite images, how to perform this image segmentation, how to perform this task that we needed to do in this problem, but without neural networks, without machine learning, without any of these crazy techniques. Yeah. And apparently, fact that we have not just RGB, but RGB plus M-band plus infrared and all the other stuff, and fact that, let's say, water and vegetation, they react to this type of this like frequencies in a different way, allows you to identify some type of the classes in unsupervised way. So if you look at the like picture on the this like equation in the bottom, yeah, what does it tell you? You take on the pixel level, you take values of the green channel, of your near infrared channel, like do the difference and like divide by their sum, just pure pixel value. That's it. You can find all water in these images without any networks, without any fancy techniques, and that's what is represented at the right. So this like yellow big thing, it's like a river, and plus there's a lot of false positives about buildings on the top right, but they can be filtered out based on the area, because I mean buildings are small, rivers are big, and this was our way to get like to deal with like water. And if you do it in this question, top right, no, there were some buildings that had like blue roofs for sure. Yes, swimming pools. It's Nigeria. Strongly doubt. So I mean, that they have swimming pools and spas all over their villages. So I mean, and this was our way to identify water, just like this simple approach. And of course, it's not like so we did this investigation, but for other participants, one of like some other our friends, he wrote a kernel on the Kaggle that shows, and basically it's actually like picture from his kernel how to do it. Yeah. And if you use this technique, you use his kernel just purely without any neural networks, without any GPUs, without any fancy software, you're able to get like 90% of the running water and 60% on the slow water. And this automatically, without anything else, gives you in the top percent of the leaderboard at the Kaggle. Yeah. So what I'm trying to say, don't ignore simple classical methods. Sometimes they're better, sometimes they're faster, especially when you don't have enough data to deal with. Okay, so now we're done with cars. We didn't do anything about them. Not like 2 water classes, they were done in this way. Okay, next slide. As I mentioned on the previous slide, we use thing named NDVI, which is like green channel minus infrared divided by their sum. Yeah. And when we looked at the literature, there were like, number of other ways to do it. And there were like some other indices that tried to like increase contrast of vegetation and probably like roads, soil and things like this. And these are 4 examples that we were using. We didn't use them like to identify like trees and vegetation. I mean, we tried, but it didn't work that well. But what realistically we did, we used them as extra channels to our neural network that I'll talk a bit later. So here I just want to say that on the next slides, you will see this NDVI, YEVI, SAVI, CCSI, and other like unclear letters, and they really like mean something like this. You take different channels in your images, divide or subtract some simple combinations, and they increase contrast of some type of the classes. Okay, so for other classes, for buildings, structures, crops, trees, and something else I already forgot, we use neural networks. Why? Because I mean, these days when you say computer vision, you mean like neural networks. When you say neural networks, in most of the cases, you also use computer vision. Because out of the box, they show really good performance, a lot of literature, very exciting, things are great. And yes, and for us, it also was the case. So on the top, you can see pipeline that we were using in this like short to go from these raw images in these different like channels and to get like mask at the left. So what did we do? We take RGB, we take P, which is panachromatic, like gray image, high resolution. We took M band, we expanded this. Then we dropped A band. Again, like we were like pretty generous in terms of dropping information in this problem. So we dropped A, and we added this stuff that I showed in the previous slide as an extra channels. So unlike standard computer vision problems, when you have only like 3 channels, R, G, and B, on the input we had 16. Yeah. Another thing, like these images are pretty big, something like 3600 by 3600. Yeah. There is no like, we didn't have like any GPUs, and even if we would, it would be unwise to do it and fit all this image at a time at the input. So what did we do? We just like cropped like small patches, like 112 by 112, generated batch, and in this problem, large batch showed like better performance. Then we did like, we applied to each patch random transformation from the group D4, symmetry of the square, meaning like rotations, flips, no rotations, like flips, rotations by 90 degrees, and inversions. And as an optimizer, we used Nadam. And we trained, initially we trained one network for all these classes, and this is good enough to get into the top 10%. Yeah. But top 10%, it's not our level. We should go higher. Yeah. I mean, and to do it better, you need like to be more specific. So, and what did we do? So, as you've seen on the previous slide, classes are really different. Crops are big. I mean, a lot of them, like, buildings are small, roads are small. And our belief is that if you train one network to predict all classes at some, it gets confused because class imbalance is that big. I mean, solution for this was just like to have one network per each class. One for buildings, one for trucks, one for roads. And yeah, when we later on analyzed behavior of the loss on all these classes, it looked pretty different. So yeah, and like we believe that nearly everyone at the top used the similar approach, at least like second, third, and fourth place, and fifth. They were doing something pretty similar, one network per class. Yeah. Okay, so question. So about RGB and P. So when you take like normal like picture of you with your cell phone, you get RGB, and this is high resolution RGB. Satellite images, they don't work this way. You were taking high resolution P panachromatic image. I mean, satellite takes it. Then it also takes low resolution M band, yeah? And then it combines them with precision and pan sharpening. They take low resolution M, high resolution P, and you get like high resolution RGB. Okay, so yes, like after you do pan sharp, so question is after you do pan, so you use P to recreate RGB from M. I mean, do you really need to keep it like, well, because it doesn't carry any extra information, everything is incorporated in RGB. This is true, you can drop P, but we didn't do it. Initially we thought like, let's drop RGB because it was like not original, it was recreated from M, and we tried different combinations. In practice, we believe that just it didn't really matter that much. Training was really noisy because data is different, because some other issues. So all these changes about do we need to keep RGB or do we need to keep P, or do we really need like to add this AV and DVI and other indices as extra channels, changes were not that big enough for us to make some decision about do we need to keep it or not. Yeah. So unlike other Kaggle competitions, when you fight for like fifth digit after the decimal point, like at the top here, it was not the case. Difference became like pretty like clear, and in the top 10 places, difference between like scores, it's pretty big, much bigger than like standard things that you have. Okay? Sure. Uh-huh. Okay, so question is understand like how to do validation, yeah? So about validation, this like problem validation was tricky, and to my knowledge, no one figured out how to do it properly. Reason for this is because, as I described before, like no, you can do validation. There are different ways to do it. You can like divide pictures. You can even like try to divide them in a more stratified way, saying that like in the holdout set, percent of crops is the same as train set. Or there was like another bright idea that we tried, again didn't work that well. You use for your train set, you say 4/5 of each images, and for validation, like 1/5 of each image, and you crop randomly. This is train, this is validation. And this works pretty well when you do big changes. Let's say at the leaderboard, when you go to point 1 to point 2 or point 2 to point 4, for sure, increasing like in this validation gives you like in like leaderboard. But because again, like train and test, they're so different, fact that you have stable validation at your train set doesn't mean that it will correspond to improvement of your model performance at the test set. So yeah, about validation, what did we do? I mean, we were like training model, more or less, at least train set will goes to the plateau. After this, we looked visually, like if our network is like, does it look better or worse? And if we believe that that our predictions worth checking, we were checking, like submitting them to the public leaderboard. Yeah. But in terms of this like numerical validation techniques, to my knowledge, nothing worked that well to capture small changes in your model performance. Yeah. Okay, so neural network architecture. Every paper, every post, everything should have similar picture, a lot of layers, something is going here, something is going there. So this network architecture is named UNet, although I believe Facebook reinvented this and named it Sharp Mask. But I mean, what does it really mean? So network architecture is similar to what you see for like autoencoder. You have encoder, you have decoder, so your input and output have same size, and here you also add skip connections, which are borrowed from the idea about ResNet to make it stable. This architecture performed really well last year at some competition, Data Science Bowl 2016, I believe. Also, I used this network architecture and I got 10th out of 900 for this ultrasound nerve segmentation. Basically, it converges better than its competitors for this amount of data and this type of the data. We tried like a lot of different architectures, dense net for segmentation, I don't remember, like whole like list of them, but either they were converging slower and just it was too slow for our fast iteration approach, or the accuracy was not high enough. So we used this like relatively simple architecture that worked really well. Yeah. Next trick and next idea that we used, when you use image segmentation and your classes are mutually exclusive of your like prediction, as an output you use sigmoid, and as your loss function you use whatever you use, binary cross entropy, average binary cross entropy. I mean, if your classes are mutually exclusive, you use whatever, categorical cross entropy, and if they're not mutually exclusive, binary cross entropy, and this works really well. But we in competitive environment, we need to do better. We need like to squeeze another part of the performance, and like one way to do it, and it was also shown in other competitions, just you modify your loss function. It is well known in competitions and industry, and I believe in academia also, that you get the best results when your evaluation metric, way that your results are evaluated at the end, and your loss function, things that you optimize for, they're as similar as possible. Yeah. Basically, I mean, we know this example, like for those that do ads, you can optimize for click-through rate, but at the end of the day, you really want like to measure your impact in terms of dollars that you get from this like ads that lead to some purchases. And this is a mismatch between this like click-through rate, what you optimize for, and what people buy. It adds some complications in business. There's a lot of work, and I believe AdRoll is working hard, and they overcome these issues. Yeah. Okay, so what I'm leading to, our evaluation metric was average Jacquard. Yeah, and it would be great to optimize directly to the average Jacquard. But Jacquard index is measured on the binary values. So it takes your ground truth, which are zeros and ones. It takes your predictions that are zeros and ones, calculate the intersection, divides by the union, and this gives you Jacquard index. Problem with this that this quantity is not differentiable. And to use backpropagation, to use like anything that optimized with stochastic gradient descent, you need something that can be differentiable at least to the first order. And solution for this was to take this like Jacquard that is defined on the binary values like zeros and ones, correct versus wrong, and generalize it to the case where your prediction is probability, some value from 0 to 1. So you take binary Jacquard, you generalize it, it becomes differentiable. We just like also took logarithm for sanity, and this becomes your loss function. Yeah. So all these like big equations at the bottom, it's just generalization of your Jacquard, and it allows your network. Now you can take your network and directly optimize for your evaluation metric. I'm not saying that it will give you that much, but I mean probably if you wouldn't use this, would be like 8th or 10th or 15th. Yeah. And using this approach, using this trick, we got like third. Yeah. And overall, yeah, if it's possible to optimize to have your loss function and evaluation function as close as possible, go for it. Yeah. Next slide. We take your network. So how did we do predictions? As I mentioned before, we have original images at 3600 by 3600. Our network takes as input as an output something like 112 by 112. And it means that to perform prediction on these big images, you take this big image, partition this into tiny tiles, you make prediction on each of them, then you combine it together, and you get something picture like this. Doesn't look bad on the one side. You can see some structure here, some roads, some trees, some buildings probably, but there's like something clearly like rectangular there, solidly clearly rectangular, some kind of artifacts that it would be nice to overcome. And here, like later on, like on the next slide, I'll talk like how did we overcome this limitation. But here I want to emphasize that like in industry and also in competitions, visual inspection is very important. If you can like visualize what are your prediction, it can be distributions that you predict or like actual pictures that you're doing. Like, I mean, if you don't do it, you will not perform well. Just if you can see with your eyes and add your domain knowledge, it's good. So we got this picture and we want to like do something about it. So what did we do? This problem was mentioned in literature. I mean, everyone knows about this, and there were a couple papers that do some kind of numerical investigation. Idea is you have patch in the input, you do something at the output, but not all regions in your predictions of your network are as equal and as equally good. Center of your prediction is decent, but when you go to the edges, you get some kind of like boundary condition, boundary artifacts. So like on picture on the right, you can see log loss error for class buildings on the train set as a function of the difference distance from the center. So center of this image is center of your like prediction, what your network predicts, and edges are its like sides. And as you can see, error stays decently constant in the central region, but then when it gets to the sides, it grows exponentially. Yeah? And this was the like reason why we got the square all over the big image. Yeah? To overcome this, typically in literature, people either crop this prediction, they do prediction, then they crop edges, or they do some kind of overlaps instead of like pure tiling. But we did it in like, I believe, nicer way. We modified our network that it would predict cropped images. And this solved a couple problems at the same time. We got better convergence because backpropagation was based on less noisy mismatch in your prediction and actual ground truth. And also, I mean, automatically was taking this like things into account. Yeah. Okay. Next slide, and we're almost there. So again, as I mentioned, on the left, you can see how we took this picture and we partitioned this into tiles and make prediction on each tile. But to do this, we need to be able to take our image and divide into the integer number of tiles, because each network takes as an input this 112 by 112. But our original images, they're not divisible by this number. And as a solution to this, you do some kind of like padding on the sides to make it like increase its size to make it better. And of course, yeah, in the beginning, in the middle, you see how we went from some kind of like bottom right corner of some image, and so we added some padding on the sides, zero padding, And this allowed us to like divide this into patches. And when we make predictions, situation again became bad. Reason for this, we believe that our network, when it sees this image and it tries to predict something at the edges, it sees this like sharp change in gradient of the pixel values from the central image to the zero padding region and says it is sharp, it is wall of the building. And it predicted us on the old perimeter of the building, small of the image, small layer of buildings. And some other artifacts like this that we like, identified with the visual inspection. To get rid of this, we replaced zero padding by reflection padding. You see on the right, it's the same at the center, but like central part is mapped to the sides, worked amazingly well, no artifacts on the sides, good quality predictions, worked really well. Yeah. So it's like another trick. It doesn't give you that much in terms of Kaggle scores, but if it's add you something, it adds like solidly. Yeah. Next slide. So here we want to show like another way to improve your performance. So this is kind of schematic. I was like kind of tired into all of these like satellite images, and I created this Akela from the Jungle Books, from the Jungle Book. So what I'm trying to show with this scheme, you have your network, you have predictions, it does something, but your predictions, they have some kind of variance. You're all familiar with like bias variance trade-off and all these like beautiful words, yeah? So you can decrease prediction of your variance. And for those that participated in some other competitions in which you need to do like stack XG boosts and all these other things, maybe you did some blending or maybe like bagging works on this idea. If you take predictions that made on the same data set but in a different way and take the average, your score goes up because variance of your predictions decreases. And you can do similar things with images. When you do classification, way to do it, you take some images, you do 10 random crops, you do prediction on all of them, make average of them, and this is your prediction for this image, and this is better than if you just took only one. And here we use similar trick. So you take your satellite images in this like sense, it's wolf here, you rotate them, then you like pad them, then you split them into tiles, make prediction, and then you rotate them better and you take geometric mean. Geometric because we're predicting probabilities. Yeah? And result is better. You get better quality of the predictions. Your masks on your satellite images are more clear, more like contrast. And this adds you not that much, but probably like from 0.1 on the leaderboard to 0.2, which is probably like another 20 places, it can easily give you. Yeah. Okay, and basically that's like we use these tricks, we use this approach, we use this network architectures, and this is what we got. On the right, RGB image corresponding to some area. On the left, our prediction. And as you can see, it's not that bad in a way. You can see roads, you can see like lakes, you can see buildings probably, trees, man-made structures, things like this. And it's not like exceptionally good image as people tend to show usually. It's pretty average. Maybe not even the best, but it has like whole reach of different classes. That's why I represented here. Yeah. And in some sense, yeah, it's good enough to get the place. Okay. So summary, we had 10 classes. 2 of them were cars. We dropped them and didn't predict. 2 of them were water classes, and we used this NDVI index to predict both of the water classes, and it by itself is good enough to get in the top 50% of the leaderboard. For other classes, we trained separate network for each class. Yeah. One for buildings, one for man-made structures, one for everything else. On the input of each network, we had RGB, P, M, that is like stretched to match RGB size, and for indices NDVI, CCSI, XAVI, and EVI, something like this. Important thing about hardware, because typically people ask, like if they don't have experience or maybe they will have experience and they want to work on a similar problem, what is about your hardware? I mean, we both have pretty like good desktops. Yeah, I have Titan X at my desktop at home. Sergey has GTX like 1080. I'm not sure that like he used all 128 GB of RAM. I'm pretty jealous to this. But yeah, but overall, it's more than enough to perform well on this type of the problem. Probably if we had like worse GPUs, we would move to the cloud just because, not because you need a lot of GPU and a lot of hardware to create your final solution. But in the competitive environment, your result is proportional to how many attempts, to how many tries do you do per unit of time. Because as you all know, like 1 out of like 100 ideas work, and to get this one idea, you need to check another 99 also. And this means that you need like to iterate fast. Like you do some network, then you try another optimizer, maybe you change receptive field, batch size, all set of like different parameters. And some of them perform like better, but these days when you work with deep learning, there are some heuristics, some nice ideas, but it's mostly experimental stuff. Yeah. Okay, I believe that's it. Questions? Sure. Okay, so what do you do with the errors and labeling? So if there were some papers and some literature about this, and people are studying this with respect to ImageNet, and they claim, and I tend to believe. So first of all, every data has mistakes in labeling unless it's like artificially, like synthetically generated. Yeah. And so question is like, how much does it affect your data? How much does it affect your model? And belief is that if your data is like decently noisy, like there's some kind of noise, and you have twice more data versus clean data but without noise, you'll get similar result. So if noise in the data is not that heavy, is not that big, and you have and these classes and something is well represented in this data overall, some mistakes is not a big issue. For example, if we had not 50, not 25 images on our train set, but let's say 50, probably these mistakes in the cars would not be that influential, and we would be able to get better results with it. Yeah. Did I answer your question? Okay, question? Yes, so, uh-huh. We had some ideas of, like, I mean, this problem is well known in computer vision, and in OpenCV, there's some nice functions that do some kind of things that are named morphological transformations, dilutions, erosions, and they allow to get rid of some noise and maybe made something that should be like straight, make quality of the boundaries better. We were thinking about this, but it would require here a lot of hand tuning, meaning to figure like, it may happen that like on this picture some modifications, some erosions will close the gap, but somewhere else it will, like, for road that is like thinner and maybe something else, it will increase it. It was one of the ideas that we were thinking about, but belief was that if we invest into like better training, maybe train networks a bit longer and something else, there will be no like gap here. So yeah, for sure, maybe if we had more time or more manpower and we slept less at nights, we could like address this issue much better. But yeah, and to our knowledge, other teams, other competitors, they did it. So I mean, this idea was definitely investigated. Okay, so question is, we used 112 by 112 as the input patches, but when we used such a small patch, you're losing a lot of contextual information. Yeah. And because neural networks are strong with respect to these contextual things, it would like look better if you like use bigger images as your input. And in the literature, for all these network structures, they say if you use like 200, it's one accuracy. You just like use exactly the same network like 300 or 500, you get better like accuracy out of the box. We were considering this. Reason why we used 112 like by 112 is because we believed, I mean, our experiment showed that for this data and for this task, big batch size was more important than bigger receptive field. And we used 120F as our batch size, yeah? And there was no way that using like 224, maybe 300 as like, as an input size will fit in the GPU of our memory. It can be overcame. So actually it was bothering me a lot because I wanted big batch and big receptive field, but it didn't fit into the memory of one my GPU. And as my like software, I was using Keras with Thana backend. But if you use several GPUs and use, let's say, MXNet, you can like split this batch between different GPUs and everything will fit like well. And with this logic, I bought another Titan to my computer. So now problems that I'm working on, I'm trying to do have like both big receptive field and big batch, but like we just didn't have hardware to address this. Okay, about classifications. So, I mean, for sure, classes that were well represented, for example, on this like mask on the left, you can see light green that corresponds to crops. Crops were covering decent amount of the area in the images, and that's why network didn't have that much issues finding it. For this, we could simplify network, have it like any receptive field. For crops, it worked decently well. For buildings and roads and like, even trees, situation was different. And I would want to say that if class was was represented well, there was enough of this in the train set, let's say crops or trees, network worked really well. For classes that are not like that well represented in a way that like it's only small amount of pixels that correspond to buildings, it performed worse. But at the same time, buildings has like pretty clear structure. There's like squares close to each other, some distance from each other, and there are probably some roads here and there. It was enough for the network to capture them well. So overall, I would say that although number of pixels is not that high in the data, they were captured pretty well. But at the same time, man-made structures, small number of pixels, not clear what it meant by this, and they were not captured that well. But overall, I would say like this, more pixels of some class you have, better we capture this and better network learns to how to do it. Did I answer? How did I organize my search for hyperparameters? There is a lot of packages like Bayesian opt or hyperopt, and probably you can use like randomized grid search or just grid search to optimize your parameters for like your whatever models you're doing. And when I was working on some other problems for which search is not that expensive, meaning, for example, data is small, and let's say using some kind of XGBoost like GBM or maybe logistic regression, you just can explore using Bayesian optimization or hyperopt to find some better hyperparameters. For neural networks, it's trickier. Training neural network is expensive. It takes you like another 20 hours to train a network. So you don't have the luxury to explore phase space that well. And realistically, it means what? I start neural network for like few epochs. I just like see dynamic of the convergence. And if my intuition, my gut feeling tells me that it's not good enough, I stop it. Yeah. I mean, it's named intuition and experience. And yeah, like I believe that like on Kaggle, everyone like will tell you that for sure grid search, randomized grid search, and they're great, and hyperopt and Bayesian opt and some other packages to find better hyperparameters, they work well until some point. And after this, your manual tuning can add you a bit more. And often, if you have experience with like a lot of data and a lot of different packages, you can start pretty close to this like optimal values. And but also like to address your question, like yeah, sure, we check different network architectures, different parameters, and that's where this teamwork became very like important. Because I was checking something, Sergey was checking something, and then we discussed and like discussed our next steps. And for sure, yeah. So it wasn't just like this network is good and I feel that it's good. No, like there was some like search phase in this space. Highest impact for this competition, and I believe everyone who participated knows this, to make first submission. It took me a month to make my first submission, not because problem is hard, not because something like this. This this competition will become a legend at Kaggle for the number of engineering issues that one needs to overcome to make a submission. So yeah, it took like decent amount of time to do this. And only I believe like month before the end, like community figured out how to do it properly. And yeah, we started exploring about time, like, okay, let's assume that everything is great and there's no engineering issues, yeah? A lot of time we spend, you read through the literature, but typically you don't like read every line properly. You just like look at the abstract conclusion, skim through it, probably plots, and if it looks promising, I mean, sometime you spend on implementing these networks, this architecture. So maybe like you take something that's already made by other people. We try to do transfer learning and use like weights from VGG to like create this like UNet and things like this. Didn't work. And yeah, a lot of like things like this. So something on reading. In terms of actual coding, for competitions and also like at work, I have this thing. You spend a lot of time in the beginning implementing pipeline from data, cleaning, caching, cross-validation, submission. And when it is ready, amount of time that you spend on actual coding, sitting in front of the computer and doing commits and like all these things, it's not that high because you have idea, you have pipeline, you implement this works, like you just like, do other stuff. Another thing, because networks were training for such a long time, you do two things in parallel. Network is training, you're like, reading or doing some other things. Yeah. But to split to say 20% on the reading, 80% on something else, it's really hard for me. I just don't remember because it's not really that structured. You jump from one to another all the time. Okay. Question was here? So what was our secret to do it? Okay, so question is, as I mentioned before, this competition will become legendary for the amount of pain to do a submission. And not because like, yeah, there was a lot of issues with this, but another thing, it's because you do some kind of submission, you create your masks, you do a polygon, you do submission Kaggle, and Kaggle tells you like, good luck with your life, it will not work. It's like this thing. So for example, you create a submission, and because you do this in terms of polygons, it can have like, like just submission that is typically like, some kilobytes, maybe megabytes, 5 gigabytes easily, and then Kaggle server refuses to consume it. And so question is, how did we survive? How did we overcome these like issues that are like not related to machine learning directly, but they are related to machine learning that you do at work in industry? I mean, just because data engineering is also there. I believe at some point community, and I'm not saying us, I'm saying like people at the forum, they figure out how to overcome. Belief is that Kaggle was cursing at their submissions and refused to like accept it when angles of the polygons that are created of these masks, they're too sharp. I have no clue why is it important. I have no clue how people figure this out, but this is the belief. And so how did we overcome this? We basically made all angles slightly a bit more curly, like, 1 pixel you take here, you add a bit here. So there was like another extra step just to make it more rounded in some sense. That's what people said at the forum, yes. So basically make it slightly more round, and this is passes through. But it's only about angles, and nothing is size of the submit for sure. At some point, one like Konstantin Lopukhin, he, after I asked him, he published a kernel in which he had a magic function. And after he published this, like 200 people joined the competition because it was the way to start it. It was a function that was transferring from the masks pixel-wise values that you have to the masks in a way that like it cleaned the garbage and this made the submissions not like 5 gigabytes, but let's say 500 megabytes. And after like, if you use this function, I mean, we were able to like get through the submission process. Yeah, but it's definitely the case. A lot of like people were pushed away from this problem to the 1 million data science ball or 150,000 like fish problem. Yeah, it was definitely like a thing. Did I answer it? Okay, question? Okay, so we didn't do transfer learning for all channels. There was a belief, I mean, my idea, hypothesis, that for sure water and trees and other like vegetation, crops, they would be sensitive to infrared like and all these other higher wavelength channels. But to identify cars, it may be enough pure RGB. So to just do RGB, to capture cars, at some point I created a network. I took weights from the VGG16 and I just used them for the first part of the UNet with RGB input, trying to get the cars, but this idea didn't work that well. Again, probably because I needed to constrain my face space to towns and roads and like not to look for cars in the jungles, and it may work. Yeah, but we didn't try to use transfer learning and do this transformation from like 3 channels to 20 or 16 or something. No, we didn't do it. But of course, you can like copy the weights, and from like technical point of view, you still can do it. Question is, will it work or not? No, We didn't try to like move from 3 channels to 20. No, we didn't. Because it didn't go work for like from 3 to 3, there was no point to try from 3 to 20. Okay, next question. I mean, so first of all, for sure, class imbalance is a decent issue in many problems. But what is class imbalance? For example, if your data set is big enough, 1 to 100 is not even class imbalance. That's fine. You don't need to do any like upsampling, downsampling, or any other magic. Yeah. So what did we do here? For buildings, we just didn't do anything. Because I believe context information for buildings is that rich. I mean, sharp edges, they're close together, some roads here and there. For network, network was able to capture them. And I mean, number of buildings, sure, maybe like area-wise, it's not that big, but I mean, it's still decent amount of them. They were decently well represented in the data, and they were decently similar all over train and test. So we just didn't do anything. Another thing is that for image segmentation problems, class imbalance is not such a big issue as it can happen for classification. Because I believe that probably number of outputs for your image segmentation is so big that some kind of averaging is happening there. Maybe if we had less buildings, we would try to do something else, or maybe we give up as cars, or maybe we do some kind of downsampling, or maybe we can do some kind of histogram matching to find most promising regions. Basically, if you have some some region in which green is too much, probably it's jungles and you don't need to look for buildings there. We didn't do it. It out of the box worked really well. Yeah. One more time. What's the question? Oh, so I mean, sure, there is again a lot of literature to do some kind of attention and region proposal to first to find, let's say, if you need to find cars or maybe buildings, to find the most promising regions in the picture and try to use your networks there. And it definitely helps. We didn't try to do it. First of all, I've seen a lot of literature about this when they talk about image localization, and basically, faster RNN and SSD and other networks, they work in this direction. But I didn't see anything about this for image segmentation. Maybe I didn't look carefully, and there was definitely nothing about this about satellite image segmentation. So we didn't do it. Probably it may be as a promising direction, and if I work in a company that is doing this, and I was doing this on the everyday basis, I can look at this. But because you do all this fast iteration, switching time, you in San Francisco, Sergey is in Siberia, forth and back, trying to address a lot of questions at the same time. And really, in terms of how much time did we spend on this, about is this more or less intensive work. So okay, I spent 1.5 months to do first submission, and then we joined into the team, and for the last month, we worked extensively together on this more scientific way, iterations, papers, blog posts, and there were some interesting ones. And yeah, so basically idea looks interesting, but we didn't check. Question? Okay, about winning entries. So I know what second place did, and I know what all people with Russian names, and there was a lot of them in the leaderboard. I know what all of them did. I mean, because we discussed, we were curious. There was even some guy, his solution, he didn't have GPUs or neural networks. He's but I know how to use XGBoost. And he used XGBoost. And you know what? He probably in top 20. So I mean, it was very surprising, but whatever. If you can get in top 50% purely on this NDVI, let's add XGBoost and we'll see how it will go. So yeah. But I mean, about first place, I don't know. This guy Kyle, he lives in Malaysia, so we don't have access to him as a part of the Russian community, and he didn't write anything at the forum at all. So I mean, this is mystery. Probably Wendy knows, but it's NDA or classified or something like this. No, you don't know. Did he publish? Okay, so hopefully, because I already submitted our blog post with our description with more words, details, and pictures to the Kaggle blog post, and Megan said that. What? It's strange. I mean, I submitted this yesterday, and then probably like someone need to like check my English because it's not that great as I would want. I mean, so probably yes. So if Kyle is going to publish something, we will know. If not, like we didn't go to Malaysia and talk to him. But like, yeah, I don't know any other better ways. Okay, other questions? Okay, yes. So in some sense, organizers, they did on the one side pretty good like job in terms of like anonymizing images, because like if you know where it is, you can add like some kind of extra domain information. You can start cheating using OpenStreetMaps and other things. And so, but like organizers like did pretty good job in terms of anonymization, so we didn't know where it is. We guessed it's Vietnam, because I am in jungles, rice fields, and I don't know, in Russia, we got told that this is happening in Vietnam. No idea. But basically, after the end of the competition, like one of the participants, I believe he finished like 11th or 10th, like, hey, Kaggle Grandmaster, he shared like with us that it was like happening in Nigeria, and also like said where exactly it was. Yeah, but we didn't use this like information, and hopefully it's good. But I need to add like way that organizers anonymize this data, added extra pain in terms of this like engineering and how to make this first submission. Yeah, but overall, like I mean, there was good anonymization, and we didn't know that it's like Nigeria. I mean, like you can find this information on the forum, but he had like thought, like domain knowledge, some like knowledge of geography, intuition, luck. Yeah, he shared some steps that he did to find it, but yeah, we didn't know this. Question? What current competitions I'm most excited about? Right now, I'm the most excited about ImageNet. That is not Kaggle competition, but like sadly, it's happening like not during the summer as usual. It's happening exactly right now, and I'm looking into the data. In terms of Kaggle competition, of course, like entertaining one is one with this like sea lions or something like this. Nice pictures, looks good. People are excited. Competition about Amazon forests, I didn't look at, but so far it looks like straightforward as a MNIST. Basically, if like you guys, some of you never tried deep learning as a competition about this, like Amazon, like forest prediction looks the most straightforward. You come home, you spend 15 minutes, you start your network training. It's like, I mean, for me, it will be that straightforward. No like extra engineering pain. MNIST replace digits by, this like forests, and it's going. Yeah, seriously, like no lying. What other competitions do we have? Something about concert there. I didn't look, but guys said the date is decently noisy. But in some sense, I want to say thank you to Wendy and other people that work in Kaggle that finally, after all these years of predicting like insurance and like insurance claims and some other things that are probably very exciting to someone, but like not really, we started like these days on Kaggle there's a lot of deep learning competitions. It may make some people upset because they may probably don't have enough hardware, but I mean for me it's very exciting. It's like interesting area, and you're not fighting for the fifth digits after the decimal point, and you can actually see what you're predicting. So overall I'm kind of happy there's a lot of deep learning competitions happening right now, but I don't have any particular that I'm excited about it yet. Maybe in couple days. And I'm saying in couple days because we submitted this blog post to Kaggle yesterday. So we're working on this now, after all write-up is like done, probably time to start coding. So yeah, you can ask me like in couple days and I can tell you what like is the most exciting competition for me right now at Kaggle. Sure. Question? Okay, about Kaggle, I mean, it's well known, like, and probably everyone who tried to work hard on Kaggle will agree, Kaggle is second full-time unpaid job. Without any jokes. Yeah, it burns a lot of time. I mean, as a side effect, in terms of good, like, when you start working your first competition, you like don't know what's happening, issues, Kaggle, coding, packages, networks, committing, like all these things, how to structure your work. And it takes a lot of time. But like after first 20th, 30th competition, half of this you already did, it becomes half automatic, and you don't spend that much time on actual coding, but you just do some kind of like still like literature and investigation and to see what changed since last time you worked on a similar problem. So in terms of time, a lot. For this competition, in like last months, all weekends, all evenings. Plus, to make it more efficient, I had alarm and woke up twice at night to check how my network is like going. And if something is wrong, restarting this. But I mean, this started after we got like in the top 10 like area, and you can feel that it's not just like just for knowledge. You have some chances to win or something. So yeah, and this like, paid off. Do you want to say something here with the microphone? Yes?
I just want to quickly say thank you for joining. I'm Wendy. I'm the organizer and designer of the competition, and I'm sorry for the submission errors. Sometimes I have to fight very hard to, some competitions are not a fit for a Kaggle, and this is kind of an example of it really wasn't a fit, but I push very hard because I think it's an interesting problem. This is not my talk. I'm sorry. I'm not going to take questions. It's just my lift is arriving. And we'll talk about it later. It's not my meetup. Sorry. I just wanted to say thank you. And sometimes I do fight for these weird competitions because I like the weird competitions, but I know that they would be a pain to join. But I thought the geometry is fun. And I kind of just know like it's just going to be a pain, and I'm going to take a lot of blame on the internet. But I'm glad that you had fun. People seem to have fun, even though there's a lot of complaints. As saying hi to the internet people that might be watching this. So thanks.
Okay, guys, I think that's it. Thank you.